Welcome to the first video in SL09. In this section of our class, we'll be thinking about what happens adjacent to carbonyls. And the focus here conceptually will be that the carbonyl itself will influence what can happen at adjacent types of positions. And in particular, what we're going to focus on is carbons that are adjacent to carbonyls. So one of the things that we've learned as chemists, starting in about the 1920s, is that this position that's adjacent to a carbonyl has protons, or could have protons, you can imagine structures where this wouldn't be true, that are actually surprisingly acidic. So the pKa of one of these protons is about 20. Approximately 20. So remember, we're using a rounding system, so anywhere between, let's say, about 17 to 23 for aldehydes, for instance. And we'll see that the pKa changes a little bit depending on the kind of carbonyl functional group we have. So let's compare that to the analogous hydrocarbon. So here, our pKa would be about 50. So what we can conclude here is that the carbonyl is actually acidifying those protons nearby by 30 pKa units. 30 doesn't sound like a large number, but remember that pKa, this P is telling us we're dealing with logarithmic units. So these protons here are 30 orders of magnitude more acidic than these. So what we can conclude here is that carbonyls make their adjacent protons much more acidic. Well, why do we care? It's like a kind of a non sequitur, right? We've talked about lots of different compounds with different acidities. And that's because of the structure of the conjugate base for these types of compounds. So if we think about drawing an acid-base equilibrium where we remove one of these protons that's adjacent to a carbonyl, then we end up with a structure that has a carbanion in it. So one of the two protons in this particular molecule get removed, we would have a lone pair on carbon, and that carbon would become negatively charged. So we have what we would call a carbanion. And this carbanion has a special kind of a name. These are enolate structures. And so this term gets used whenever we have a carbanion adjacent to a carbonyl. So if we think about the structure of our enolate, or in other words, the conjugate base of these kinds of aldehydes or ketones or esters, whatever, a couple of things pop out, right? We can actually look at the structure and make some decisions about the kinds of roles these structures would actually play in reactions. So these enolates are, not to be too cute about this, they are probably going to be bases. That would basically mean running this reaction backwards, where we put a proton back on. Based on the pKa of this structure, 20, we know that this is a pretty weak acid. There are weaker acids in the world, but this is not particularly acidic. We've seen lots of compounds with pKa's that are smaller than 20. And that means that the corresponding conjugate base, the enolate, is going to be a relatively strong base. Remember that weak acids give rise to strong conjugate bases. So this is going to be a strong base. And if that's true, we usually also observe a correlating role, that these types of structures, these enolates, will be good nucleophiles. And in particular, this concept that we can use these enolates as good nucleophiles is actually quite important for us. Because if we look at this, we have a carbon that's nucleophilic. And we don't really have that many ways to make carbon nucleophilic. So earlier in the semester, we talked about Grignard reagents and organolithium reagents. And in those cases, we could make good carbon nucleophiles, but that involved using a halogen. Where does the halogen come from? You have this open question about how you use this, and it's not necessarily that general. There's lots of types of Grignard reagents that would be hard to make or aren't stable. This is a different way. That if we could actually take compounds that have carbonyls, we could deprotonate adjacent to the carbonyl, to make these enolates and then use the enolates as nucleophiles. So it's kind of a complementary strategy for making new bonds to carbon. And if you think about it, organic chemistry has a lot of bonds to carbon in all of the different kinds of reactions you've studied. So this is a really important idea for us. It's one of the reasons why enolates are so important. And what we'll see over the course of this video series is that not only do people use enolates as nucleophilic carbon, but nature does also. So in the next section of this video, we'll be taking a deeper dive into the structure of enolates to understand why placing a carbonyl adjacent to these protons makes them so acidic relative to simple hydrocarbon components. So if we look at the same kind of acid that we saw in the previous section of the video and its corresponding conjugate base, we might be able to make some decisions about why this proton is relatively acidic relative to other kinds of CH bonds. And in particular, as we've talked about earlier in the semester, we want to focus on the structure of the conjugate base itself and analyze stability of charge buildup. So that basically means that I need to be focusing on what is happening to the lone pair that I'm getting on a carbon and whether or not I can stabilize the lone pair. The more I can stabilize the lone pair, the more acidic the structure becomes. Another way of thinking about that is if you make this compound and specifically the lone pair stabilized, you provide a reason for this compound to be willing to lose a proton. So that means I'm going to have to break out my tools with respect to induction and resonance. And if I think about these kinds of compounds, we've been focusing on what the carbonyl is doing. So I'm going to focus my analysis on the substituent here, the carbonyl, adjacent to the charge that we're developing. So if I look at the carbonyl, I know that it's an inductive acceptor of electron density, and that should lead to some withdrawal of electron density from the negatively charged carbon. So one feature is that the carbonyl is an inductive acceptor from negatively charged carbon. The other thing I could consider is that the lone pair that I've placed on carbon can actually be delocalized. So there's resonance in which I can place the lone pair onto the oxygen. So I'll draw the resonance structure here. That gives me 3 lone pairs on oxygen, a CC double bond. And so here, what I can see by drawing this is that I moved electrons from the carbon, where the lone pair was, onto the oxygen. And that means that the carbonyl is actually a resonance acceptor. From our carbon. So I'm seeing 2 different mechanisms by which the carbonyl is actually stabilizing the lone pair that develops on this carbon if I were to deprotonate this particular carbon, the CH there. So I both have inductive stabilization, or accepting from the carbon, and I also have resonance stabilization, or accepting from the carbon. And those are both going to lead to a much more stabilized negative charge than I'd be able to achieve in the absence of the carbonyl. So these 2 features combined basically allow us to make some kind of explanation for why it should be relatively feasible to generate this carbanion ion. Remember, this is still a fairly unstable negative charge, but it's stable relative to a case where the carbonyl didn't exist. So at this point, I want to layer in a little bit more nomenclature because it's going to be a little confusing going forward if I'm always talking about adjacent carbons. You can imagine in some kinds of functional groups like ketones, there might be more than one adjacent carbon. We have a nomenclature system that talks about the proximity of a carbon in a chain to a carbonyl. And in particular, we use the Greek alphabet. So the first Greek letter is alpha, and the first carbon away from the carbonyl is going to be called the alpha carbon. The next carbon away from the carbonyl will correspond to the second letter of the Greek alphabet, which is beta. And the third carbon away from the carbonyl down the chain will be the third letter of the Greek alphabet, which is gamma. And so on and so forth. So if you had a longer chain, you'd have a delta position or a delta carbon and an epsilon position or an epsilon carbon. For the purposes of this class, we'll largely be focused on the chemistry of the alpha carbon. which is the one that we mean by saying adjacent. So our alpha C is adjacent to carbonyl. And in the SLO after this, we'll be looking at the chemistry of the beta carbon. So I want to tie together a few ideas here, and I want to layer in this language about the alpha carbon. So we know that the alpha carbon has an acidic proton. I know that the alpha carbon can be nucleophilic. But for this to be true, it has to be deprotonated. And the final thing that I want to note is that the alpha carbon, because it's nucleophilic, can be functionalized. What I mean by that is that we can essentially substitute an alpha hydrogen, so like the proton attached to the alpha carbon, for other types of groups. If we take advantage of the fact that removing the alpha hydrogen gives us a nucleophilic carbon, I should be able to put electrophilic groups onto the alpha carbon. So that's what I mean by functionalized. Convert from a CH to a C something else. So our alpha carbon can be functionalized by reactions with electrophiles. So these three ideas about the alpha carbon, and specifically what happens to the alpha carbon, both as a consequence of the carbonyl acidifying its proton and what the alpha carbon can do once it has been deprotonated, will form the basis for the entire SLO that we'll be working on this week. In the next section of this video, we'll be looking at some kinds of specific details for how chemists go about generating enolate structures, so the conjugate base forms of our structures like this, as well as look at an example where we would want to generate an enolate from a specific compound here. Unlike the last section of the video, we'll now be looking at a ketone, but the important thing to recognize is that there is an alpha carbon that has a proton. So in a ketone here, we have two different alpha carbons, here and here, but only one of them has a hydrogen. So I'm really just focused on trying to remove this proton. Well, I need a base, and that's really what this section of the video is about. What kind of base should I use? So we could choose like a base that we're all familiar with. If I asked you if we were in class together and I said, what's your favorite base? I'm sure someone would say hydroxide, and I'd say something like, wow, you guys are so boring. But guess what? We're going to do hydroxide anyway. So OH minus, we've got a bunch of lone pairs on oxygen. And so we know that there'll be an acid-base equilibrium here, where we will remove the proton from the alpha carbon. That will place a negative charge on carbon. That's going to make our enolate. Okay, here's our enolate. If you'd like, you could draw it in its major resonance structure form, which would be a CC double bond and an O minus. That's fine. So this would be the major resonance structure form of an enolate. You could draw either of these two. Remember that there are two different ways of representing the same structure. But we also have the conjugate acid of hydroxide, so we're going to generate a water molecule. Okay, so just so you get a little bit of practice reminding yourself about assessing the favorability of acid-base reactions, what I'd like for you to do is to predict the position of equilibrium here. Another way of saying that is estimate the KEQ value. Will it lie mostly toward the products, the reactants? Will there be no preference at all? So pause your video and assess KEQ now. You could approach this in two different ways. You could actually look at structures where you would analyze relative charge stability of OH minus and the enolate. That could be challenging because we have a bunch of different structural variables. We've got resonance, stabilization in the enolate. There's none in the hydroxide. Here, O minus, or oxygen, is always negatively charged. In the enolate, oxygen only carries some of the negative charge. So this is a difficult comparison to do from a structural perspective. But we do know pKa values for the relevant protons involved in this kind of reaction. So we would need to look at pKa's of the acid and the conjugate acid. So we know water, pKa here is 14. And we talked about these alpha hydrogens being about 20. So for aldehydes and ketones, that's a pretty good estimate, as we'll see later in this SLO. Ester alpha hydrogens and amide alpha hydrogens are a little bit higher in pKa. So our proton here is, let's say, about 20. It looks to me like I'm actually generating a stronger acid on the product side than I had in the reactant side. And that means that this equilibrium is likely unfavorable. So I'm just going to adjust my equilibrium arrows a little bit so that we can show that graphically. We have a little bit of forward and a lot backward. And if you wanted to, you could even estimate a KEQ value for this. It's going to be about 10 to the negative 6th, so 14 minus 20 as the exponent. So this reaction does form enolate, but only in very small amounts. And that's kind of a general takeaway, is that if we use bases like hydroxide, that we actually generate small amounts of enolate. Moreover, this formation of the enolate is reversible. This concept of reversibility will be important shortly in this video. So what if there was some application that you had, whatever it is, maybe you're making a molecule, and you couldn't have this enolate formation be reversible. You needed to make sure that it went all the way to the right, that you took this compound and you removed the alpha hydrogen from essentially every single molecule of your starting, in this case, ketone. Well, you would need to use a stronger base. So we would need to use something other than hydroxide. So if we took the same kind of a reaction, so I'll redraw the acid, and we wanted to do this deprotonation. At this point in the semester, we've learned about a lot of different kinds of bases. So what I would encourage you to do here is pause your video again, and if you need to, go back into your lecture notes and find other strong bases that you think that would be sufficiently basic to essentially irreversibly or completely favorably deprotonate this structure. So you probably noticed when you went back through your notebook that we've actually talked about a lot of bases this semester. So let's look at a little bit of a list. Our list O bases. You might have had something like methoxide, so MEO minus or ETO minus. The so-called alkoxide bases. I would argue that these structurally are quite similar to hydroxide. You've got a localized negative charge and an oxygen, and no other real structural features that are stabilizing or destabilizing that negative charge. So these compounds have conjugate acids that are alcohols that have pKa's around 15. So we can start doing our pKca. Here, this is 15. Remember, water would, if this were on the list, would be 14. So what other bases do we have? Oh, triethylamine, net 3. That's, you guys like that one? Net 3. So if I put a proton on net 3, I'm going to have an ammonium ion, pKa of about 10. Okay, so neither of these bases will work. I need a number for a pKca that's larger than 20. Let's see, what else do we have? Oh, I know. How about some good old Na, right? Sodium hydride, so that might work. Here we have H minus, and the conjugate acid would be H2, and we'll approximate the pKa for H2 at 35. Okay, so that might be an option. Na. The other base that you might have noticed, although this came up only in passing earlier in the semester, are if we have deprotonated amines, so N minus. So for instance, NaNH2. So in this case, the nitrogen's negatively charged, and the conjugate acid here would be like ammonium. So we're adding a proton, but the nitrogen will become neutral. Very different from a tertiary amine that's going to become an ammonium ion. So here our pKa is again about 35. And then if you were feeling very clever, you might have thought about, oh, well, what about Grignards or organolithiums, right? So we have what I'll write as RMGX, so Grignard or RLI. That would be something like an organolithium. If this is for some simple alkyl chain like, I don't know, methyl lithium or ethyl magnesium chloride, your pKa would be the hydrocarbon itself. So this is a pKa of 50. All right, so we've got a few bases here. These ones, whoops, that's not what I wanted to do. We've got a set of bases. Our alkoxides and our triethylamine, these aren't strong enough. And it turns out that we're going to run into an issue with our Grignards and our organolithiums too. These are both bases and nucleophiles, but this is a rare case where these compounds will be better nucleophiles than they are bases. This is essentially contradictory to what you learned about carboxylic acids in these compounds. And this is kinetic in origin, so these compounds will definitely deprotonate at the alpha position, but they add to the carbonyl faster. So we actually find that these act as nucleophiles, not bases. And that means that if we wanted to irreversibly deprotonate this type of a ketone, these two bases would be good options. And in particular, what modern chemists will typically use is sodium hydride. It's a little bit easier to work with. So what would this look like? So I would treat my ketone with some H- from Na, and I'm going to need to make a little bit of space to show the products. So I'm going to erase my list now. The joys of working with a tiny board. And this really isn't even going to be in equilibrium, because when I make my enolate, I'm going to also make H2. This is a gas. So we've got two things that are driving this reaction forward. One is that the pKa here is 35. pKa here is 20. And these are approximates. So there's a 15 order of magnitude driving force toward the products. And as this reaction goes forward, H2 is leaving the reaction. So I'm both favoring this based on relative acid strengths and also by the fact that I'm removing gas product from the reaction. So this deprotonation with sodium hydride is irreversible. So we've got two different methods to make enolates, either a reversible method using things like hydroxide or potentially alkoxides, ETO-, MEO-, those kinds of things, or with sodium hydride, or I guess you could use sodium amide, so NH2, and those are going to be irreversible. So depending on what kind of reaction you're trying to accomplish, one or the other of these methods may be more valuable, and we'll talk about that in more detail later in the SLO. So in the next section of this video, we'll be looking at another wrinkle for enolate generation. So let's say you wanted to generate the enolate from this ketone. So this is a different kind of a ketone from the previous section of the video. One thing you might notice, though, is that we're going to have an issue. How many alpha carbons are there that have alpha hydrogens? Well, if I look at the structure, I know alpha carbons are going to be the carbons that flank the carbonyl. So I've got an alpha carbon here and an alpha carbon here. And if I look at the structure carefully, I'll notice that while this carbon has 3 different hydrogens, so this carbon has H's, or we have alpha H's here, and so does this carbon. I'll draw one of them in. So where would we actually form the enolate? There's 2 possible structures here. So if we actually took this compound and reacted it with sodium hydride, we would form 2 different kinds of enolates. this structure, and this structure. So we get what are called regioisomeric enolates. What we mean by that term is that these two structures are isomers, and they differ only in the placement of functional groups. So is the alkene on this part of the chain or this part of the chain? So these are regioisomers, regio, like region. We've got one enolate that has like a carbon-carbon double bond that's in the interior of the chain, and one where that double bond is on the exterior of the chain. So this double bond is more substituted than this one. And it turns out that if you do this reaction with sodium hydride, one of these two enolates is preferred. It's this one. So this enolate is major, and this enolate is minor. And it turns out that there's a few ways we can explain this. So this enolate is more substituted. And this enolate is less substituted. What we mean by that is that there are two non-hydrogen substituents, not counting the oxygen, so 1, 2, on the carbon-carbon double bond. In the comparison structure, there's just one non-hydrogen, non-oxygen substituent. So you learned about this back in OChem 1, that alkenes, which are not exactly enolates, but do have carbon-carbon double bonds, that those tend to be more stable if you have more non-hydrogen substituents. And the same idea holds true for our enolates. So our major enolate is more stable. So some language you may have learned last semester, maybe not, is that whenever we have a situation where we can form two different products and we actually need to decide or talk about which one of them is favored, there's a couple of different ways we can talk about this. If nature, essentially, or the reaction, made the choice on the basis of structural stability for products, we talk about the reaction as being thermodynamically controlled. Thermodynamics is essentially the study of structure and stability. So we call this enolate the thermodynamic enolate. The other way that reactions can make decisions is by not caring about how stable the products are, but caring about what reaction of competing processes, so like does H- react here or here, which of those reactions happens faster. We call that kinetic control. So kinetic control you could think about as a game of Hungry Hungry Hippos, which is maybe something you played with your siblings or maybe your parents. The idea is that you like slap a hippo's butt as fast as you can, and there's a direct correlation with how many times you slap the hippo's butt and how many marbles you collect. So the faster you slap, the more marbles you collect. In a reaction, the faster the reaction goes, the more product that reaction will form relative to the other reactions that are playing the game. So it turns out that this enolate we can form under kinetic control. And so we'll call this the kinetic enolate. Generally speaking, the kinetic enolate is going to be the less substituted of the two. And generally speaking, the thermodynamic enolate is going to be the more substituted of the two. So let's look at how we would generate a kinetic enolate. From a strategic perspective, it apparently is the case that regardless of rates, at least with this base, we're going to make the more substituted or the thermodynamic enolate. So I have to come up with some way to override the intrinsic preference of the reaction for the more stable product. Basically, another way of saying that is I need to slow down the formation of this structure relative to this one. That's what it means to actually operate under kinetic control, that we're using reaction rates to pick products, not stabilities. So if I think about what's happening in this reaction, my base is either going to have to interact with this proton, and if I interact here, I'll get the major, or sorry, the thermodynamic enolate. If I react here, I'll get the kinetic enolate. What if I chose a base that was really big, like in a size sense? Because if I have a really big base, I'm going to have more of a problem reaching this proton. I'm going to have to navigate around this part of the chain. That's going to be like slapping the base away. But on the other hand, this proton on the outside of the molecule, much easier to access. And that's actually how we do this. So we're going to choose what's called a bulky or a sterically hindered base. Right, you might have heard the term bulky base here. These two terms mean the same thing. So I want to have an atom that's basic, and I want to put large groups on it. But I also need to make sure that the atom that I'm using as a base is sufficiently basic to irreversibly deprotonate the alpha position. If I allow for equilibration or reversible proton transfer, all reversible processes are intrinsically thermodynamically controlled. And now I've lost control over my problem. I'm going to end up with a thermodynamic enolate. So I need to use a sterically hindered base, and I need to use a base that will irreversibly deprotonate the alpha carbon. So I can't use sodium hydride. I can't attach anything else to this hydrogen, but the other base that we talked about in the previous section of the video was sodium amide, or NaNH2. So what if I took those H's off of the N and I replaced them with large groups? So we're going to modify NH2 minus, so the structure. This nitrogen is where my base strength comes from. So I'm going to keep the N minus part, but I'm going to replace these hydrogens with something that gives steric hindrance as it tries to approach these protons that are buried in more complex parts of my structure. And in particular, maybe I could just add some big alkyl chains onto the nitrogen in the place of these hydrogens. All right, so I'm going to keep my nitrogen, two lone pairs, negative charge. That's my source of very strong basicity. And I don't know, how about some isopropyl groups? Those seem good. So I've got a CH3, 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 CH3. Okay, so let's look at the structure just to make sure that we're all on the same page here. So this part here, the N minus, that's my strong base. And these isopropyl groups are my steric hindrance units. So two different kinds of functions that I want that are baked into the structure. This is rationally designed from first principles the way we just did it. So this compound usually gets used as the lithium salt. So you have the N minus and a lithium plus that are kind of interacting with each other in an ionic way. And this compound is going to be called lithium diisopropyl amide. So that's kind of a mouthful. We call this LDA for short. So the structure of LDA here, it's a little bit marked up, but you can see it's two isopropyl groups with a nitrogen that's negatively charged, and we call this a kinetic base. It's going to generate the kinetic enolate. So this is an important takeaway. LDA will select for, that's not how you spell for. I'm having a lot of spelling problems today. I wonder why that is. Kinetic enolate. So that solves our problem here, where for whatever reason we wanted to do chemistry with our kinetic enolate, we would use LDA instead of sodium hydride. So this structure is kind of fun. You don't necessarily need to memorize it, although it's good to have a general idea for where it comes from, so these design ideas. I had a student a few years ago who for whatever reason, really wanted to remember the structure, and so she actually ended up calling it reindeer attack. I guess because these isopropyl groups reminded her of like antlers, but I can't look at the structure without thinking reindeer attack anymore. So, Anya, wherever you are, nicely done. Okay, so let's look at using LDA in an example reaction, just so you have a general sense for how you might write the structures out, for instance. So I'm going to go ahead and take our conversation here down, and we will use the same ketone. I'll redraw it. And I'll put in my protons so we can be clear. Here's LDA. And we've got two possible enolates that could form. See if I can fit them on the same line this time. That would be cool. Okay, and then we're also going to generate the conjugate acid of LDA itself. So three possible products here. This is the thermodynamic enolate, same as above. This is the kinetic enolate, same as above. And the product distribution here is 0.5% thermodynamic enolate and 99.5% kinetic enolate. So LDA is highly, highly selective. And just to remind you about why this is irreversible, this pKa is about 35. Whereas these pKa's are each about 20. So here we're not removing H2 by Le Chatelier's principle, but we're still making such a weak acid that the reaction is going to be driven to the right. So to summarize, depending on whether you want the thermodynamic enolate or the kinetic enolate, you will choose your base. So base choice dictates enolate regiochemistry. Which of the two enolates do you want to make? Depending on what you want, you choose sodium hydride or some other base that would equilibrate, or you choose LDA. Okay, so that concludes the first video in SL09. In the next video, we'll be looking at what we can do with these enolates.